All right. Hello, class. Um, I'm here with Miss Hazel. Miss Hazel is a warm doggo right now. Let's see if she wants some water. Hazel, you want some Wawa? You want Wawa, Hazel? Yeah, good girl. Hazel, get Wawa. Uh, good girl. And I'm going to turn the fan on for her. So, let's see what else is going on. I got my safety gloves for my forge today, so the pieces are falling into place. This kind of looks like the Infinity Gauntlet. Like I'm gonna snap. There we go. I just ended the universe. So I got my safety gloves. Gonna be able to handle steel at 2,300 degrees Fahrenheit. Let's see, what else is going on? I'm happy to report that Mr. Bugs is feeling better today. Hey, Sebastian. So, today I have a couple more problems. We're going to start reviewing forces today. And so let's get right into it. So in the workbook, I will be doing pages 30 through 34 today. So we have Carlos and Dominique. Again, they're using inclusive names. They're using male students, female students. They're using, Dominique, which is like a French name, I guess. I don't know. And Carlos, which is would be a Spanish name. So they're just trying to include everyone. But have you noticed that the first letters in these names are based on A, B, C, and D? Okay. So Carlos and Dominique collect the following data from an experiment where they exerted the same force F to identical sized boxes with different masses and recorded the acceleration. Okay. Plot the acceleration of the boxes versus the mass of each box. So I'm just going to do two of the points. I'm going to do this. I'm going to do this point and this point. I know that 0, 0 is going to be a point if you have a, or what am I trying to say? Actually, I'll do 3 points. Why not? Okay, so for 2 kilograms, we get an acceleration of 1.5. So that would be this point right here. For 7 kilograms, we get an acceleration of 0.4. Okay. And for 7 kilograms, or for 18 kilograms, we get an acceleration of 0.15. 0.15 would be right here. I'm going to do one more, if you don't mind. I will do this point right here. 4 gets an acceleration of 0.75. All right. So we can see there's a kind of trend line that is curved like this. Okay. Based on the graph you created in part A, identify the correct relationship between acceleration and mass of an object. So obviously the trend line is this kind of a trend line. So your answer to part B would be based on that. Based on your analysis in part B, what could be graphed instead of mass and acceleration that would lead to a linear relationship? So see how it's asking us to find a linear relationship, okay? They're asking us to linearize the graph, okay? So what we can see, we're testing F equals ma. We're testing Newton's second law, okay? So what if I divide both sides by m? So I have A equals F times 1 over m. All right? Now, what if I let my x squiggle equals 1 over m? And what if I let my y squiggle equal acceleration? So that would give me an equation of the form y squiggle equals f times x squiggle. All right? So we can compare that with y equals mx, and we see that the slope is equal to f. So that's the analysis there. So let me write that down. So I would graph acceleration versus 1 over mass. Okay? And then it says, what is the physical meaning of the slope of the linearized graph suggested in part C? The slope is the force. Okay? And the reason for that is here. Okay, we have another scenario. Angela is standing on a very low friction skateboard while Blake pushes her away from the motion detector, which is set to record the velocity as a function of time. In trial 1, Blake pushes softly. In trial 2, Blake pushes harder. In trial 3, Blake pushes Angela the hardest. Use the data provided by the motion detector to find a pattern between the change in Angela's motion and the interaction with Blake. So basically we can see that the hard push results in the steepest slope and the highest final velocity. Okay. When Blake pushes harder, the slope of the velocity versus time line is steeper. Okay. So hard to I just want to grab the text box. Since slope since the slope is steeper. Now, what is the meaning of the slope of this graph? It's a velocity time graph, and so the slope is acceleration. Since the slope is steeper, the acceleration is greater. All right. When Blake stops pushing, the slope of the velocity versus timeline becomes flat. See how this is flat. Since the slope is now 0, this means the acceleration is now 0. Okay. Students then repeat the experiment, this time. Now, by the way, what would be the slope of this line? Well, the slope is equal to acceleration, which is equal to F net over m. Okay? So we can see that the bigger the slope is, the bigger the acceleration. Students then repeat the experiment, this time with Angela holding 2 textbooks and then 4 textbooks. Sketch the diagram of velocity versus time for Angela with 2 and then 4 textbooks. Blake pushes with the same force every time. Okay, so we can see from the Newton's second law relationship that I just drew, if we increase the mass, the acceleration goes down. So, with 2 textbooks, it's going to look like this. That's supposed to be. And then with 4 textbooks, it's going to be even less steep. It'll be something like this and then flat. Okay. The following statement is written to describe what will happen after the first 5 seconds when Blake is no longer pushing. Cross out any incorrect statements and explain why they are incorrect. After you have written your answer, make sure that you check off the statements. After Blake stops pushing, Angela will travel at a constant speed for a few seconds before she runs out of force. So I would say that is wrong. Then she will decelerate and stop. So, yeah, I kind of have a little bit of a beef with this. What does it say about the skate? It says Angela is standing on a... See, I don't like this question because it says very low friction skateboard. So it's like, when you say very low, do you mean literally 0 friction or do you mean a tiny bit of friction? So I don't know what they mean. So I'm just going to explain myself. So I'm going to say if the friction equals 0, then once Blake stops pushing, this. Once Blake stops pushing, the net force equals 0, which means the acceleration equals 0, which means the speed is constant forever. If friction is merely very small, I'm going to spell it like this because I think that's a cute way of spelling small. If the friction is merely very small, once the push stops, the F net will be negative, which means the acceleration is negative, which means it will gradually slow to a stop. So I don't know. It depends on your interpretation. Let's see if I have any questions. Wait, what had happened to Bugs? Bugs was being really, hello Kyle as well. Bugs was being really sensitive yesterday. I don't know what it was. Either his stomach or his ears. Because he had dry ears. So I think it might have been his ears or it might have been his stomach. But he was making a lot of yip sounds like he was in pain yesterday. So like it was really sad. He saw a dog on the street and he barked at the dog. He went woof, and then barking made him hurt himself, so he squeaked. So he kind of went woof, he squeaked. It was really pathetic. All right, so this is the last scenario for today, I think. I'm doing 30 through 34. Okay, so yeah, this is the last scenario for today. Carlos pushes a block of mass M across a rough horizontal surface at a constant speed by applying a force directly to the right. The dot at right represents the block. Draw a free body diagram showing and labeling all forces exerted on the block. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. Okay, so we've got the applied force. We've got the friction force. Now, I'm drawing the applied force and the friction force to be equal in size. Why am I doing that? It's because you'll notice that the block is being pushed at a constant speed, okay? Which means that the net force is 0, so the horizontal forces have to be in balance. Then we have the weight force, which goes down. And then we also have the normal force, which goes up. And normal force and weight force also have to be in balance, because if they weren't in balance, the block would go up into the sky or it would crush into the ground. Okay, so I should label these, but I have not. The force going to the right is the applied force. The force going to the left is the friction force. The force going up is normal force. The force going down is the weight force. Okay, quantitative analysis. Blake is asked to use Newton's second law to derive an equation that relates force of gravity and normal force from the surface exerted on the block. Annotate this derivation by filling in the right side of the table below. For each line in the derivation, explain in words what was done mathematically. So what I would say here is we substitute the vertical forces in. For the net force in the y direction. Okay, so we notice how we just went for from some of the forces in the y direction to the actual forces, normal force and gravity. Then what we do is we notice that the vertical acceleration is 0 because the block is not moving vertically. Okay. So then we substituted in 0. I don't know, 0 times m equals 0. This third line is so basic, I'm just going to put a question mark. Like, what do you even mean? What do they even mean? That's just so basic. And then they, so because the acceleration is 0, the right-hand side of Newton's second law is equal to 0. And then that says basically we add F, the weight force, to both sides. Okay? Carlos gets tired of pushing and instead decides to pull with force F pull at an angle to the horizontal. The block slides along the rough horizontal surface at a constant speed. The free body diagram for the situation is shown below. Blake makes the following claim about the free body diagram. The velocity of the block is constant, so the net force exerted on the block must be 0. That is correct. Thus, the normal force equals the weight force, and the force of friction equals the applied force. What, if anything, is wrong with this statement? Well, one of the things we can see is that the pull force has a vertical component and a horizontal component. Okay? So basically what that means is that Newton's second law in the y direction says F net, or F normal, plus F pull in the y direction minus Fmg equals 0. Okay? So from that, we can see that the normal force equals the weight force minus the y component of the pulling, which is less than the weight force. So the normal force is actually going to be less than weight. We did this problem in class. It was the I believe it was the stubborn child being dragged by the mom. And so we're pulling upward, which means since we're pulling upward, the ground doesn't have to push upward quite as much. Okay? So that's something that's wrong with the statement. Another thing that is incorrect is Newton's second law in the x direction says that the force of the pull in the x direction minus the force of friction equals 0. Okay, so that means that the force of friction is equal to the horizontal component of the pulling force. But the horizontal component of the pulling force is actually less than the strength of the pulling force, the total strength. Why is that? It's because the leg of a right triangle is shorter than the hypotenuse. So basically the first sentence of what Blake said was correct. The second sentence was not correct. Okay? So I have done pages 30 through 34. Hello, Izzy. And today, you guys will be doing pages 35 through 38 in the workbook. And I do want to reiterate what I said yesterday. Yesterday I said that in the event that you are too stressed out or just need a break from physics, if I'm assigning too much work, just do an amount that is appropriate for what you can do. Okay? I'm not going to penalize you for that. So just do a little bit of physics every day. Do a reasonable amount for you. I don't know how much that is. It's going to be different for every person. Okay? So have a wonderful afternoon, and maybe I will talk to you on Discord.